Welcome to Delta Wings Aviation Academy, where we prepare you for takeoff.
Hello, pilots. Welcome to Delta Wing Aviation Academy, where we prepare you for takeoff. Today, we will discuss lift explained using Newton's third law. Fasten your seatbelt as we prepare for takeoff and take a look at the overall details from the sky. In my previous video, we looked at how lift is generated using Bernoulli's principle. Now, let's understand lift from a different and equally important perspective, Newton's third law of motion. You may have heard about the Venturi effect and how it plays an important role in generating lift, especially in a teardrop-shaped wing. As the airflow speeds up over the curved surface, the pressure decreases and lift is produced. But now you might ask an interesting question. What about lift in a symmetrical wing, where both the upper and lower surfaces have the same shape? We commonly see symmetrical wings in aerobatic airplanes performing barrel rolls, nearly symmetrical airfoils in helicopter rotor blades, many fighter jet wings, even paper rockets. So, how is lift generated in these cases? This is where Newton's third law of motion helps us understand what's really happening. In this video, we'll break this concept down step by step and clearly see how Newton's third law plays a key role in lift generation. Newton's third law states, for every action, there is an equal and opposite reaction. Many people think airplanes fly because the top of the wing is curved. Upside down, they shouldn't fly. Reality. Lift comes mainly from angle of attack, airspeed, air density, wing area. Wing shape helps, but it's not required. The lift equation is where rho equals air density, V equals airspeed, S equals wing area, CL equals lift coefficient, wing shape, angle of attack, and flow conditions. Before we start, let's clarify a few things. A symmetrical wing means the upper and lower surfaces are identical. When we say the wing is flat, we mean it has a zero angle of attack. It is not tilted relative to the airflow. Symmetrical wing, moving forward, no angle of attack. Imagine an airplane moving forward through the air with a symmetrical wing, meaning the upper and lower surfaces of the wing are mirror images of each other. When this wing moves straight ahead, flat, zero angle of attack, it is aligned parallel to the oncoming airflow. As the air reaches the leading edge, it splits and flows around both the upper and lower surfaces of the wing. Some of the air is pushed slightly backward in the direction opposite to the aircraft's motion, which creates drag. Here's the crucial point. A flat, symmetrical wing at zero angle of attack cannot generate significant lift. It mostly moves the air sideways around its thickness. Only a very small amount of air deflection occurs, so there is no net downward push on the air, and therefore almost no lift. Now think of lift in the simplest possible way. A wing moves up only if something pushes it up from below. That something is the air. According to Newton's third law, when the wing pushes air downward, the air pushes the wing upward with an equal and opposite force. With a flat, symmetrical wing at zero angle of attack, the air is not pushed downward enough, so the upward push on the wing is very small, or nearly zero. To actually generate lift, we need to change the situation. We do this by tilting the wing upward relative to the airflow, which is called increasing the angle of attack. When the wing is tilted, it forces the air to flow downward as it passes the wing. The air pushed downward pushes back upward on the wing. That upward push is what we call lift. In short, if the wing doesn't push air down, the air can't push the wing up. So what do? You are right. We induce an angle of attack. The pilot controls this using the elevator, a small movable flap on the tail. Pulling back on the elevator raises the nose of the aircraft, increasing the wing's angle of attack relative to the oncoming air. With a higher angle of attack, the wing pushes more air downward as it moves forward. This increased downward deflection of air produces a stronger upward reaction, the lift that allows the plane to fly. According to Newton's third law, action, the wing pushes air downward. Reaction, the air pushes the wing upward. This upward force is lift. In simple steps. 1. The pilot moves the elevator, which tilts the nose of the airplane upward. 2. This increases the wing's angle of attack, causing the wing to push air downward. This is the action. 3. The air pushes back upward on the wing, generating lift. This is the reaction. The greater the downward deflection of air, the more lift is produced, allowing the airplane to climb or stay airborne. 4. Summary, cause, and effect. Flat wing to minimal or zero lift. Air just hits the leading edge. Tilted wing to air, push downward to lift generated elevator input to pilot controls. Wing tilt to controls, angle of attack to controls lift. So in essence, lift is all about deflecting air downward, and Newton's third law explains exactly how that works. Real-life example of lift. Let's see a simple, real-life example. Your hand out of a car window. If your hand is flat, the air mostly flows around it. You feel almost no lift. If you tilt your hand upward, the air is deflected downward, and you can feel your hand being pushed upward by the wind. The airplane wing works the same way. The pilot uses the elevator to tilt the nose, which increases the wing's angle of attack and causes the entire wing to push air downward. Just like your hand, the reaction from the air lifts the whole wing, not just the leading edge. Wait, the video isn't finished yet. Let's see where people misunderstood. Many people think airplane moves forward, air flows over the wing. Laminar flow at the trailing edge pushes air down, and that makes the leading edge lift up. They're very close, but let's make it precise. Key correction. The reaction is not just at the leading edge. The entire wing experiences an upward force. That's lift. Let's break it down step by step. As the airplane moves forward, air flows over and under the wing. Near the wing, the airflow is often laminar at first, then becomes turbulent farther back. But lift does not depend solely on laminar flow. It depends on the wing turning the air downward. Because of the angle of attack and the wing's shape, air is turned downward along the whole wing, not just at the trailing edge. The trailing edge is just where the downward airflow finally leaves the wing. That's why we see the downwash. Action. The wing applies a force to the air, accelerating it downward, changing its momentum. Reaction. The air pushes back upward on the wing. This upward reaction force is lift. Important clarification about edges. Incorrect. Trailing edge pushes air down to leading edge lifts up. Correct. The wing as a whole pushes air down to the air pushes the wing up. Lift is distributed across the entire wing surface, although pressure differences vary along the wing. Finally, let's compare lift on cambered and symmetrical wings. We'll see how lift works and how wing shape affects it using Newton's third law as our guide. 1. Cambered airfoil, teardrop. Shape. Curved on top, flatter on the bottom. Lift at 0-degree angle of attack. Yes. Mechanism. The curved shape naturally deflects air downward, generating lift even without tilting the wing. Lift comes from both wing shape and angle of attack. Performance. Works well at low speeds. 2. Symmetrical airfoil. Used on fighter jets, aerobatic planes, some helicopter rotors, paper rockets. Shape. Top and bottom mirror. Each other implies no built-in curvature. Lift at 0 degrees angle of attack, minimal or none. Mechanism. Lift occurs only when the wing tilts into the airflow, positive angle of attack. The wing deflects air downward, and by Newton's third law, the air pushes the wing upward. Step-by-step example. 1. Symmetrical wing at 0 degree. Air splits evenly, no little or no net lift. Pilot pulls back on the elevator, nose rotates upward, angle of attack increases. 3. Wing deflects air downward, air pushes wing upward, lift is generated. Key point: the pilot controls pitch altitude, not lift directly. Lift arises automatically once angle of attack is set. 3. Upside down flight, symmetrical airfoil, generates the same lift upright or inverted. Cambered airfoil requires higher angle of attack or speed to produce lift when inverted. Physics: lift comes from air being tilted downward relative to the wing, so orientation doesn't matter. Analogy: hold your hand out of a car window, tilt it slightly, then it rises. Flip it upside down and tilt it, still rises. Quick comparison table. Takeaway: lift doesn't require a teardrop shape. It arises whenever a wing deflects air downward, which can happen through wing shape, angle of attack, or both, creating the necessary pressure difference and upward force. Why symmetrical wings are used: predictable lift upright or inverted, ideal for aerobatics and fighter jets, handles high angle of attack safely. One sentence summary: in a symmetrical airfoil airplane, the pilot increases angle of attack using the elevator, which pushes air downward and generates lift. This is why airplanes can fly upside down. Lift depends on angle of attack and Newton's laws, not wing curvature alone.